Welcome to The Debate. Today we are looking at a silicon computing chip that is, well, quite literally alive.
Yeah, it sounds like pure science fiction, doesn't it? A completely inorganic, sterile environment just suddenly merged with wet biology.
Exactly. We are examining a truly unprecedented development from Australian researchers at a biotech company called Cortical Labs.
Right, the CL1 chip.
Right. They have successfully trained what they call a biological computer. So, specifically, it's a CL1 silicon chip integrated with approximately 200,000 living human brain cells. And these cells were actually derived from human blood stem cells.
And to push that sci-fi element even further, they haven't just kept these human cells alive on a circuit board. They have actively trained them to play the chaotic, three-dimensional 1990s video game Doom.
Which is wild. But it brings us to a profound crossroad, and really our central question for today's discussion. Does this successful integration of living neurons into a digital environment represent a viable, revolutionary paradigm shift for the future of highly efficient computing and artificial intelligence?
Or, on the flip side, do the inherent biological limitations of these cells restrict this technology primarily to the realm of medical modeling and neuroscience?
It's a massive question for the future of the tech industry.
Oh, absolutely.
So my position is this. The integration of living human neurons into the CL1 chip represents a transformative, sustainable leap forward for computing, offering real-time, goal-directed learning with an energy efficiency that traditional silicon simply cannot match.
And I come at it from a different way. While this is a fascinating biological achievement, the inherent fragility, short lifespan, and frankly, erratic outputs of living cells mean this technology is fundamentally ill-suited for practical computing. Its true value lies strictly in disease modeling and healthcare research.
So to understand why I see this as such a monumental paradigm shift, we really have to look at the mechanics of what these 200,000 cells have actually achieved on that chip.
Right, the actual gameplay.
Yeah. According to Alon Loeffler, the senior application scientist at Cortical Labs, these neural cultures started exactly how you would expect a cluster of cells to start, basically at the level of a total beginner who has never played a video game.
Yeah, they were essentially fumbling in the dark, right? Walking into walls, just shooting at nothing.
Exactly. Because Doom is not a simple flat environment like Pong. It is a chaotic 3D world where the user must explore their surroundings, interpret spatial data, and actively dispatch enemies.
Sure.
But through the CL1 chip, they adapted. They eventually started targeting enemies regularly and correctly. This is real-time, goal-directed learning happening on a biological neural network.
But let's clarify exactly how a cluster of cells sitting in a dish actually, sees a 3D video game. Because they obviously don't have eyes.
Right. That is where the hardware comes in. The CL1 chip uses a high-density microelectrode array.
Okay.
Essentially, the digital telemetry of the game, so the location of the walls, the proximity of the demon, the position of the player, is converted into spatial temporal patterns of electrical signals. The chip physically zaps specific regions of the cell cluster to represent that digital environment.
And in return, the cells fire back electrical impulses, which the chip then translates into digital keyboard commands, like, move left, move right, or shoot.
Precisely. It is a closed-loop system. And here is the crucial metric that makes this so revolutionary. The human brain operates on an estimated 20 watts of power.
Which is incredibly low.
Right. We are talking about a level of energy efficiency that modern silicon computing and artificial intelligence desperately need, but fundamentally cannot replicate with rigid logic gates. As Cortical Labs Chief Scientific Officer Brett Kagan points out, this is a more sustainable and more powerful form of intelligence. We aren't just observing biology, we are harnessing it for computing.
Well, I certainly acknowledge the scientific novelty of it. Observing synaptic plasticity, actual biological matter rewiring itself to react to digital stimuli is undeniably fascinating.
It's huge.
It is. But if we are evaluating this as the future architecture of computing and AI, we have to look critically at the severe, inherent limitations explicitly noted in the research.
You're referring to the biological overhead.
First and foremost, yes, these cells have a 6-month lifespan. We're talking about a computer processor that literally dies a few months after you manufacture it.
Well, yes, but
And furthermore, the material clearly states that this system is not yet capable of producing consistent, programmable results. I mean, if you watch the actual gameplay being touted here, it's not a clean execution.
it's chaotic, sure.
Very chaotic. A single demon in the game takes several attempts to slaughter. The cells fire wildly in multiple directions before the target is finally hit.
I see why you think that, but let me give you a different perspective on how we evaluate nascent technology. I think you're judging a proto-technology by the standards of a highly mature one.
How do you mean?
Let's create an analogy here. Think back to the early days of silicon computing. The ENIAC, the early vacuum tube computers.
Oh, the room-size machines?
Exactly. They were massive, they consumed absurd amounts of power, and they constantly broke down because the tubes would literally burn out,
Sure.
and their outputs were incredibly limited and prone to error. You could easily have looked at a blown, shattered vacuum tube in 1945 and said, this is too fragile to ever be useful. But we engineered our way to the microchip. When we look at the biological computer, we have to look at the trajectory of innovation.
But the trajectory here is governed by biology, not metallurgy or physics.
But look at the progression. These same cells previously mastered Pong, a simple 2D game where a paddle moves up and down. Now they have moved into Doom, a complex 3D environment.
Right.
The thousands of tiny dots monitored on the researchers' screens represent genuine adaptation to digital stimuli. The progression from 2D linear tracking to 3D spatial navigation and enemy targeting proves that the fundamental mechanism of biological computation works. The sloppy gameplay isn't proof of failure. It is a proof of concept.
I'm sorry, but I just don't buy that. Let me tell you why that vacuum tube analogy completely falls apart when you look at the biology.
Okay, go for it.
When a vacuum tube broke, it was an engineering failure that could be solved by better materials, which eventually led to solid-state semiconductors. But comparing biological cells to early silicon ignores the fundamental nature of what is actually happening on that chip.
How so? The cells are processing inputs and delivering outputs.
But we need to explain why they are delivering those outputs. This relies on what neuroscientists call the free energy principle, pioneered by Carl Friston.
Right, okay.
Biological systems inherently want to minimize surprise. They want a predictable environment.
Right, they seek homeostasis.
Exactly. So the researchers use that. When the cells miss the target in the game, the microelectrode array hits them with random, chaotic static, unpredictable white noise.
Which the cells hate.
They hate that. When they successfully hit the target, the array delivers a clean, highly predictable electrical pulse. The neurons literally rewire their physical synaptic connections simply to avoid the chaotic static.
Which is learning. They are adapting their physical structure to achieve a specific goal.
But what we are observing is basic biological conditioning. It's essentially habituation to an electrical stimulus. That is entirely different from programmable computation.
I wouldn't say entirely different.
I would. Silicon executes a programmed logic gate flawlessly, billions of times a second. These neurons are essentially being prodded with electricity until they twitch in a direction that happens to correspond with a digital gun firing.
That's a bit reductive.
It's like trying to train a cloud of gnats with a laser pointer. They cannot execute cleanly because biology at this scale is inherently noisy and stochastic, not deterministic.
That's an interesting point, though I would frame it quite differently. You are treating the noisy or stochastic nature of biology as a strict negative, like a flaw to be engineered away.
Because in computing it usually is.
But in the realm of modern machine learning, rigid determinism is actually becoming a massive bottleneck.
Wait, are you arguing that we want our computers to be inaccurate?
I'm arguing that we want them to be adaptable. Look at how we train traditional AI models today. They use complex mathematical algorithms like gradient descent to learn.
Right.
But they frequently get trapped in what are called local minima. Basically, the AI finds a solution that is good enough and gets stuck there, unable to see that a much better solution exists just over the horizon.
Right, so engineers have to artificially inject noise or temperature into the algorithm to bump the AI out of that rut.
Exactly. We are spending billions of dollars and massive amounts of computational power to artificially mimic the exact kind of neural noise that these living cells produce naturally for free.
For free is strong term.
Well, biologically speaking, biological neurons have leaky ion channels and synaptic fatigue. They are naturally stochastic. This leads directly to the most pressing crisis in modern tech, which is power consumption.
The gigawatt data centers.
Yes. William Keating, the CEO of semiconductor research company Ingenuity, asserts very clearly that this is not wacky science and that the industry desperately needs better ways to manage its power envelope.
Yeah, the demands are astronomical.
Modern AI data centers require gigawatts of power, demanding specialized liquid cooling infrastructure, and they are literally pushing our electrical grids to the brink. I mean, we have companies looking to power their data centers with dedicated nuclear reactors.
It is undeniably a massive logistical and environmental crisis.
So how can we dismiss a system that operates on a microscopic fraction of the power of traditional AI? If a biological cluster can learn spatial navigation and problem solving on merely 20 watts of power, the efficiency of a human brain, that efficiency alone dictates that we must pursue it as a computing architecture.
20 watts is appealing, sure.
Power consumption is the primary bottleneck of the 21st century.
That's a compelling argument, but have you considered the actual holistic cost of running a biological system?
In terms of maintenance.
Yes. The human brain runs on 20 watts, and yes, the purely electrical power envelope of this chip is tiny, but you are ignoring the biological overhead.
The life support, essentially?
Exactly. Let's look at the strict 6-month lifespan of these cells. A silicon processor sits in a server rack for a decade. It requires only electricity and air cooling, and it functions identically on day 1 as it does on day 3000.
Well, usually.
This CL1 chip contains living tissue. A computing component that literally dies means it requires intense biological maintenance.
Cortical Labs is already building automated incubator systems to handle that, though.
But think about what that entails at scale. You have to incubate it. You have to maintain absolute sterility to protect it from pathogens, because a bacterial infection will literally rot your computer processor.
Right, it's organic.
You have to constantly cycle in a liquid nutrient medium to feed the cells and remove cellular waste. And after all of that, you have to completely replace the processor every 6 months when the cells undergo apoptosis and die.
It is a different kind of infrastructure, certainly.
It is an infrastructure that entirely negates the benefits of its low electrical power consumption. It makes it completely impossible to scale for widespread commercial use in the tech sector.
I don't know about impossible.
You cannot build an exascale AI data center out of components that need to be fed, risk getting infected, and have a biological expiration date.
I'm not convinced by that line of reasoning because it assumes our ability to maintain biological systems will remain static. We are already seeing rapid advancements in automated biomanufacturing and microfluidics.
Well, sure, there are advancements.
If the core processing power is there, the infrastructure to support it will follow. And the researchers themselves see this as a foundation for broader computing.
But broader computing in what context?
Real-world integration. Brett Kagan has stated they are just scratching the surface of what these neural cultures can achieve when integrated into systems like the CL1. He specifically envisions this for real-time learning tasks that are similar to AI and, crucially, integration into robotics.
So putting a brain in a dish inside a robot?
Think about the potential. Imagine a robotic system navigating a real-world, chaotic environment like a disaster zone.
Okay.
Traditional, rigid silicon programming struggles with the unpredictable, stochastic nature of the physical world. It requires massive sensor arrays and constant recalculations, but biological intelligence evolved specifically to navigate chaos.
True.
If these cells can learn to navigate the chaotic 3D world of doom through real-time feedback, they can theoretically navigate physical space. The engineering hurdles of lifespan and stability are just that, hurdles. They are not dead ends.
But we don't need to force these cells into the body of a robot to find their profound utility. By focusing so heavily on trying to make this a new form of semiconductor for the tech industry, we are ignoring the astonishing reality of what Cortical Labs has actually built.
Which you believe is strictly medical.
Absolutely.
Look at the other applications explicitly listed in the material: healthcare, medicine, disease modeling, drug screening, and personalized medicine. We skipped over a massive detail earlier. How do they get human brain cells from a blood sample?
Oh, they use induced pluripotent stem cells.
Exactly, iPSCs. You take a somatic cell like a white blood cell from a standard blood draw, you introduce specific proteins to revert that cell back into a stem cell,
Right.
and then you direct it to grow into a cortical neuron. Do you realize what that means?
It means we have a renewable source of human neurons.
It means we can grow your neurons, or my neurons. It means we can take a blood sample from a specific human being, cultivate their exact genetic stem cells into 200,000 living brain cells on a chip, and monitor their electrical activity in real time.
It's incredible.
The insight this provides into human neurobiology is totally unprecedented.
I don't disagree that the medical applications are profound. But why must it be mutually exclusive? If the chip can model diseases, why can't a scaled-up version run an AI model? Why can't it be both?
Because the foundational requirements for those two fields are completely at odds. To revolutionize traditional computing architecture, as you suggest, you need mass production, unyielding reliability, permanence, and uniform predictability.
Okay.
Biology fights against all of those things. It is inherently variable.
Which, as I mentioned, is why it's so good at learning.
But in medicine, the biological nuances, the specific, chaotic ways these cells react, degrade, or fail to fire are exactly what we want to study. Let's say a patient has a neurodegenerative disease, like early-onset Alzheimer's.
Right.
You take their blood, grow their neurons on the CL1 chip, and watch how the neural network degrades. You could theoretically model their specific biological responses to experimental drugs right there on the microelectrode array, measuring the exact synaptic response.
And you could see if the drug improves their ability to process electrical signals.
Yes. If we treat this as a replacement for silicon computing, we will constantly be fighting against the cell's nature. We will be frustrated that they are erratic and that they die in 6 months.
I see your point.
But if we treat this as a personalized disease modeling tool, those 6 months of observation are an absolute goldmine of medical data. Forcing these organic cultures into the role of a traditional computer processor is a misallocation of their true, extraordinary potential.
Well, let's take a moment to summarize where we've landed on this deeply complex issue. I certainly acknowledge the reality of the engineering hurdles you've laid out.
They are substantial.
They are the biological overhead required to keep the cells alive, their strict 6-month lifespan, and their current inability to produce entirely consistent programmable results without erratic behavior. These are significant, undeniable challenges.
It is a long road from playing Doom to running a data center.
It really is. However, I maintain that achieving real-time, goal-directed learning, having biological matter actively rewire itself to navigate a chaotic 3D environment based on digital telemetry, is a fundamental computing breakthrough.
I'll concede it's a breakthrough.
Right. The tech industry is hitting a thermal and electrical wall with silicon's power demands. Because this biological computer can operate at a power envelope of merely 20 watts, it proves that a legitimate, sustainable alternative for AI-like intelligence is not just theoretical. It is practically possible.
And I will readily agree that achieving this level of unprecedented energy efficiency while interacting in a closed-loop digital environment is a remarkable feat of real science. It is not wacky science, as you quoted earlier. It is a genuine, documented breakthrough. We are observing the physical mechanics of learning in real time.
But you don't see it running our laptops anytime soon.
No, definitely not. My stance remains that the inherent fragility, the massive biological maintenance required to sustain life, and the mathematically stochastic performance of living cells firmly anchor this technology's future in a different realm.
The medical realm.
Exactly. Its destiny is in understanding human biology. It offers an unparalleled window into advancing personalized medicine, neurodegenerative research, and drug screening, rather than revolutionizing or replacing the traditional, rigid computing architectures we use today.
It really is a fascinating intersection, isn't it? The CL1 chip sits right on the boundary line between biotechnology and computer science, challenging our foundational definitions of both.
It does.
As Cortical Labs continues to refine how they use the microelectron arrays to input data and train these neural cultures,
It's clear there is much more to explore regarding the ultimate ceiling of biological computers.
It absolutely does. The scientific curiosity driving this research is pushing boundaries we didn't even know existed 10 years ago. I mean, looking at a cluster of cells grown from blood and realizing they are seeking predictability in a digital maze, it forces us to ask what computation and indeed what learning truly is at its core.
Exactly. It brings us right back to that image we started with. For decades, we've believed that the future of computation belonged in a sterile, clean room, etched into perfect, unyielding, inorganic silicon. But now, as we watch human neurons naturally fire, rewire, and adapt to a digital world with breathtaking efficiency, we have to wonder, is the processor of tomorrow going to be built in a factory, or is it going to be grown?